When tasked with graphing a function, one way to begin is to first make a table of values. Each value in the table then determines a point on the plane. The more values that are computed, the more points that will be obtained. By plotting enough points, a discrete approximation of the graph will emerge, and, at least for functions in this course, it's not too difficult to infer how the full graph will look by a type of connect the dots procedure. This method, of computing values and plotting the corresponding points, works well for a function you've never encountered before, one whose graph is a complete mystery to you. But some functions are obtained from others by certain transformations, and these transformations correspond to ways of adjusting the shape of the graph. By understanding these adjustments, then, we're able not only to sketch the graphs of many functions quickly by hand, but also to write equations for given graphs. For example, this quadratic function looks like the power function g of x equals x squared, but it has lower order terms. By completing the square, we see that another way of writing this function is as the square of x plus 1 plus 2. With this perspective, it's clear that f is obtained from the power function g by two shifts, one on the input and another on the output. The shift on the output corresponds to a shift in the vertical direction. Because this shift is plus 2, we should move the graph of g upward 2 units. The shift on the input corresponds to a shift in the horizontal direction. Now, an interesting and potentially confusing fact about shifts on the input is that they work in perhaps the opposite way you'd expect, in that a shift of plus 1 corresponds to a shift to the left, or in the negative horizontal direction, even though the sign is a plus sign. After applying both of these shifts then, we obtain the graph of f of x. Notice that this graph looks exactly like the graph of g, but it has been shifted both horizontally and vertically according to the procedure we described. Another type of transformation for graphs is a type of stretching procedure. For example, the graph of cosine is indicated here, but if we multiply the output by 2, then the graph is stretched by a factor of 2 in the vertical direction, and we obtain a similar looking graph which now has double the amplitude of that of before. On the other hand, if we multiply the output by 1/2, then the amplitude now shrinks to half of what it was before. This stretching operation can also be performed on the input, and as before, the resulting effect on the graph can be potentially confusing. For example, if we now place a factor of 2 next to the input of the cosine function, then the graph is squeezed inward by a factor of 2. On the other hand, if we place a factor of 1/2 next to the input, then the graph is stretched outward by a factor of 2. The reason for this stretching is essentially that when there is a factor of 1/2 next to the input, then it takes twice the amount of input to move along the graph. And so when moving along the graph, the changes in value are recorded twice as slowly. This type of stretching can even be worked out when the factors are minus signs. For example, this function involves two minus signs, one on the input and one on the output. The original function in this case is the root function, whose graph we know to be this one. The graph of f then is obtained from that of g by two transformations, one for each minus sign. The minus sign on the output performs a transformation by reflecting the graph in a vertical way, that is, across the x-axis. And the minus sign on the input reflects the graph in a horizontal way, that is, across the y-axis. The result is this graph which looks very similar to that of g. Another way of thinking about the resulting graph is that it is obtained from the graph of g by rotating by a half turn around the origin. This is because such a half turn is actually the result of the two reflections we just described.